thank you very much, and thank you for this kind invitation, and it's a great honor for me to talk here at Wrocław University together, at the same session with Professor Stein. And I also would like to thank you for giving me this opportunity for some break in my bureaucratic activities. Today I wanted to start with just a basic definition of the Bergman kernel, and kind of the main theme will be the application. There are many applications of Bergman kernel, but here will be some special one, mostly in convex geometry, and so something that is that goes beyond. It's outside of several complex variables, and but there will also be the other theme of the talk will be a relationship between the Bergman kernel and pluripotential theory. And if you don't like the name pluripotential theory, you can also think of this as just in dimension one, and the relation of the Bergman kernel with potential theory. And the interesting part of this is that whereas, say, one complex variable compared to several complex variables is in most aspects, I would say, much simpler and much more developed, almost finished field in some way. But this kind of relation between the Bergman kernel and potential theory, even in dimension one, complex dimension one, has had some recent activities and non-trivial results. And it's not really, everything is not yet trivial there either. Okay, so I start with, I take omega to be a domain in Cn, and by A2 of omega, I denote the space of square integrable holomorphic functions. So these are complex valued functions on a domain in Cn, that are holomorphic on every, say separate holomorphic with respect to every variable. This in fact implies smooth or equivalently holomorphic on every complex line. And if I take a point in omega, one can easily prove that this functional that evaluates the functions at C is a continuous functional bounded. So therefore, by Riesz theorem, there exists an element which I will denote this way. Okay, and I try to make the talk as accessible to non-specialists in several complex variables as I possibly can. So if I say some too obvious things, then I apologize. Okay, the element from this space such that this functional is a product of f. And this is a standard scalar product in L2. So therefore, in other words, this is K omega is this is the Bergman kernel. This is really defined by this reproducing property. Maybe let me rewrite it. So F W is equal to the integral of f of z k omega zw bar lambda of z for any w in omega and f in the Bergman space. All right, so that's the definition, and I'd be almost entirely interested during this talk in the Bergman kernel on the diagonal. Okay, so k omega at w. Well, from this reproducing properties follows immediately that it's, if you just take as an f, this functions, this is square of the L2 norm, and so this is really the square of the norm of this functional. So the most useful definition for us is that this is a supremum of f of w square over this is the L2 norm taken over all square integrable holomorphic functions that are not zero. Well, I assume it's a domain, so not everywhere zero. So this is the basic definition for us, really. We are interested in the Bergman kernel on the diagonal. And I'll be talking on some estimates for this. And right away, you see that a lower bound for this requires a construction of some holomorphic function. So in order to estimate the Bergman kernel from below, you always have to construct some holomorphic function. And the philosophy when constructing holomorphic functions in several complex variables, you really have to solve the d-bar equation. But I will not really talk, so the d-bar equation will be hidden in this talk somewhere. And Professor Stein will talk more on the d-bar equation or d-bar operator. But okay, I will emphasize when it's where and when this is hidden. Now, okay, so that's the Bergman kernel, and now let me give you an introduction to the Malheur conjecture. So this is convex analysis. Assume that K is a subset of Rn. It's that'll be a convex, symmetric around the origin. So K is minus body. By body, I mean it's a compact set and has non-empty interior, and I assume it's convex. So this is, in fact, such objects are equivalent to norms in Rn. So just any such a thing gives you a norm in Rn whose unit, and this is the unit ball of this norm, and this norm is really the Minkowski functional of this body, which maybe I will write down. Q of x is the infimum of t bigger than 0. X over t is in K. Are equivalently a supremum of this is the scalar product, x dot y. Y is in K prime, where K prime is the dual, where K prime is the dual or a polar body. So all y in Rn such that x dot y is not bigger than 1 for all x in K. All right. And now, if you take a product of the volume, so this will be a volume of K, and take a volume of K prime, this is an interesting object. This is called a Malheur volume. So this is interesting in particular because it's invariant under linear transformations. Therefore, it's also invariant. I mean, it does not depend on the scalar product that you have there. So it's really some kind of Banach space invariant of Rn, of this Rn with this norm given by the Minkowski functional. So apparently, it's an interesting object for specialists in those finitely dimensional Banach spaces, which I know nothing about, frankly. But there are two, well, say, questions on when this number is maximal and when it is minimal. So it's well known when it is maximal, and this is so-called Błaszke-Santalo inequality. It was proved by Błaszke in dimension 3 and by Santalo in general. I think Santalo proved it in 1949. And it says that the Malheur volume is maximized by balls. Okay, so it has a maximum value for balls, and therefore for all ellipsoids. But it's also important that balls are the only maximizers. So that's somehow all right. And then there is a question of the lower bound, and this is still an open problem. This is so-called Malheur conjecture. I think formulated in 1938. And it says that it should be, let me write it, it's minimized by cubes. It is true in dimension 2, true for n equal 2. In fact, the proof is quite simple. You take polygons and you modify them, reduce the number of vertices, and eventually end up, and then you show that by this process you decrease the Malheur volume, and you eventually end up with parallelogram, which is a cube, which is really a square. Right. But much more complicated things go on in higher dimensions. So let me, and in fact for n equal 2, well, a square is the only minimizer. But if you take n equal 3 and k just a cube, then one can show that, well, it's just this is like L infinity norm, so this is given like by L1 norm. So this which is the octahedron, right? So we have a cube. Here, sorry, I cannot draw. So, and we have the octahedron. Right, so like two pyramids, and then also here. Now, and the point is that, you know, in dimension 2, you have a square. If you have a square, then the polar is well, a square again, so that they are equivalent. But those two are not linearly equivalent. And of course, the Malheur volume of both has to be the same. So it shows you already the difficulty, because if Malheur conjecture is true, cubes cannot be the only minimizers. And the general, so it's conjectured, still unknown, that in dimension 3 these are the only two, and in higher dimensions these are so-called Hansen-Lima bodies that are produced from lower dimensional, either produced by lower dimensional bodies by taking products or by taking duals, as here. And they should be the only minimizers. But this, for example, shows you that it's impossible to prove it by some kind of a flow of something that would converge to one good object. And okay, but there is an important, again, that's what I've been told, because I'm not an expert in this, but important result, partial result, it's Bourgain-Milman inequality. It's 1987. And it says that there exists a positive constant such that the Malheur volume for such bodies as there, so convex symmetric bodies in Rn, is bounded from below by c to the n times, well, 4 to the n over n factorial. This is the volume of the cube. So Malheur conjecture is equivalent to proving this estimate with c equal to 1. That's so Malheur conjecture. Now, the original proof was so there was no specific value of c given, but the best one obtained so far is by Greg Kuperberg, who is Polish, I understand, by living in the US, but son of two well-known Polish mathematicians. 2006. And he proved it with a constant pi over 4. Okay, but to me, this whole business was, I got interested in that because a few years ago there was a paper of Nazarov who did two things. So first, he he gave an equivalent several complex variables formulation of the Malheur conjecture, and this I will equivalent formulation. But he also gave a complex analytic proof of the Bourgain-Milman inequality, although with a worse constant than Kuperberg. But his main tool was Hermander's estimate for the Debar equation, and really the main point was a lower bound for a Bergman kernel. So I will come back to this. But let me first show you, I think this is an interesting direction, potentially even maybe possible to prove the whole conjecture using this complex analytic approach. I don't know. Okay, but let me first show you how this works. So now I try to give you the link between this and several complex variables. Okay, so I have this body in Rn, and I take an L2 function, complex valued, arbitrary L2 function on the dual. And I consider the Fourier Laplace transform of this. So this is the integral over k prime u of y e to my I y z d lambda of y. So this is really an entire, this is a compact set. So this is really an entire holomorphic function, right? In fact, from any distribution with compact support, you can, the Fourier transform or Fourier Laplace transform would give you an entire holomorphic function. Now, if you evaluate this function at the origin, say take a modulus square, so this is precisely this integral. Now, if you use the Schwarz inequality, so we consider this as 1 times u. So this will be bounded by the volume of k prime times the L2 norm of u in k prime square. But this, of course, by the Plancherel theorem, this is equal to, well, the constant is 2 pi to minus n, the volume, times the L2 norm of this u hat, but, well, evaluated not on the entire Cn, but that would not be possible, but on just the real axis. Okay, you can consider Cn as Rn here and then imaginary axis here, and so this is just the L2 norm evaluated on the real axis. All right, so thank you for that. And we also, the equality holds if and only if this is if this function is constant. So if equality holds, for example, for the characteristic function of k prime. So therefore, I can write and that's the main point, is to express the volume of the dual in terms of something that does not, that gets rid of the dual, really. So therefore, the volume of k prime, if you look at this, you can write as 2 pi to n, and then the supremum over a certain family of entire holomorphic functions. More on this in the moment, times, well, the value at the origin, times f of x squared d lambda of x on Rn. So it's almost like the Bergman kernel, and you want to but it's the only difference is that you don't take all holomorphic functions. We'll see which ones just a moment, and just those transforms that you obtain this way, and that you take the integral only, the L2 norm only on the real axis. So where this class P is the set of all functions obtained by taking duals of square integrable functions on K prime. But now the point is, by the really Pauli-Wiener theorem, you can precisely describe what this function is, what this family is, and it consists of those entire holomorphic functions that satisfy two things. So first is that there is a uniform bound with some positive constant C e to the Q. So this is, it's like this second expression for the Minkowski functional. So this really comes from here, and here you have the Minkowski functional, but just for K, not K prime. That's important. And secondly, that, well, those integrals are finite. So that's our. You can easily show using the Pauli-Wiener theorem that this class P is precisely characterized this way. That's well, quite elementary, if you will. So this means that to prove the Malheur conjecture, it is equivalent to construct an entire holomorphic function with certain properties. So let me write them down precisely. So Malheur conjecture is equivalent to proving the following statement. There exists so for every convex symmetric, let me write for every K, there exists a convex symmetric body. There exists an entire holomorphic function such that, well, say the value at the origin is 1, and well, it satisfies this uniform bound. So this will be the only condition on K. F of Z is bound C E Q K, the imaginary part of Z. It's and so this is, and then the last condition is that this denominator in this expression is bounded from below by a right constant. It should be precisely n factorial pi over 2 to the n times the volume of K. So of course it's a more complicated formulation than the problem itself, but I think it's very interesting because, well, first of all, you get rid of the dual here, and secondly, it really boils down to finding a holomorphic function, which in several complex variables is really to solve the bar equation. And there is a really a big abundance of tools in several complex variables. I think missing maybe in convex analysis, like various estimates for the d-bar equation. So, okay, this approach has not been continued yet, but I think it's promising, especially since there have been some useful d-bar estimates generalizing Hermanders proved recently. Okay, but using kind of a similar idea, let me also show you some, say, positive results. So that is this proof of the Bourgain-Milman inequality. All right, so the theorem of Nazarov. Okay, K is again convex, symmetric body in Rn. And okay, so this time we don't take the Fourier Laplace transform to go into the complex word, but we take a tube domain. So the domain omega, this will be, say, interior of K plus I Rn. So in one dimension we a strip. So this is so if K is here, so this will be, we take the whole tube. All right. So then he proved the following two estimates for the Bergman kernel. First of all, let me write that at the origin. The upper bound he showed is the following: n factorial over pi to the n, volume of K prime over the volume of K. And secondly, the lower bound at the origin, he showed pi over 4 to power 2n, 1 over volume of K square. Now, if you combine these two inequalities, this means this is bigger than this, so corollary is the Bourgain-Milman inequality with the constant pi over 4 cube. So worse than Kuperberg's, but still some. But this is mostly to show that these methods can work. So you obtain something non-trivial in convex analysis using complex methods. That's the okay. Now the first estimate, the upper bound, is more elementary. So I will not talk about that. It really uses integral formula for the Bergman kernel for tube domains. This has been known since 60s, and some elementary estimates. But as usually, a lower bound for the Bergman kernel requires d-bar estimates, or say Hermander estimates. Usually to construct non-trivially holomorphic function requires solving PDE. Okay, and that, so originally Nazarov used the Hermander's estimate in a more kind of hidden way. But I want to show you a general result that covers, in particular, gives you this lower bound. that is so it would be a lower bound for the Bergman-Kellner in terms of pluripotential theory. But for that, I first need to define a pluricomplex green function. Right, so we come back to the complex word. So omega is a domain in Cn, and right. So let us fix a point. So we have and a pluricomplex green function. Well, in dimension 1, this will be a standard green function, negative, for me always negative. So solving an equation with a point mass for Laplacian, is a point mass at this pole, or in other words, a logarithmic singularity, and if boundary is sufficiently regular, 0 on the boundary. That's the. Now you can, for arbitrary domain, essentially you can define it as follows. So k omega the zw. Sometimes I will denote it just by gw at z. Okay, so this is defined as a supremum, and now I'm probably going into some trouble. U of z, where u is a negative plurisubharmonic function. Now, okay, I get it. So we know what a negative is, and plurisubharmonic means essentially means subharmonic on every complex line. Plus, well, in fact, the definition says it's a subharmonic on every complex line and upper semi-continuous. And funny-wise, it's still an open problem if the semi-continuity follows from the first condition. That's not the most important problem in several complex variables, but it's kind of funny that it's not known. Anyway, in other words, you can also think of this in the distributional sense. These are functions that have positive semi-definite complex Hessian matrix that's equivalent. And function that has a logarithmic singularity at this pole. So u of z is bounded by some constant plus logarithm z minus w. This constant may depend on u. Okay, not. And this you can show that in this you get the same thing as the classical green function in dimension 1. And in higher dimensions, it can also be characterized, and this is the main tool when proving something for the green functions. It can be characterized as a solution of a complex Monge-Ampère equation with the right-hand side just the Dirac point mass. Okay, now, so this is rather simple, but there is a deep result of Lempert. You know, the most non-trivial thing about the green function in dimension 1 is the symmetry. You have to use this Laplacian, really. And it turns out that in higher dimensions it's not symmetric anymore because the equation really is nonlinear. But the result of Lempert says that it is symmetric for convex domains. G omega is symmetric for convex domains. And, well, it actually says much more, that for nice convex domains, so if you have say a smooth, strongly convex, domain with boundedly smooth, strongly convex boundary and a pole, then you can always find a foliation of complex disks going through this domain, such that this green function is harmonic along every leaf of this foliation. All right, now, so this is an important object in pluripotential theory. And now, this lower bound theorem is the following. So now I'm running into even more trouble. So you have to assume that omega is pseudo-convex. And I'm not going to really give you a definition of pseudo-convex. Well, okay. In particular, well, I told you what plurisubharmonic functions are. So pseudo-convex domains are functions that in one of equivalent definitions is that there are domains admitting a plurisubharmonic exhaustion function. So exhaustion meaning every sublevel set is relatively compact. There is completely analogous relation between plurisubharmonic functions and pseudo-convex domains as between convex functions of several variables and convex domains. That's all right, and I think I only need to take a point there, and any non-positive constant, and then I have the following lower bound for the Bergman kernel at the diagonal, namely it's 1 over e to minus 2 nt times the volume of the sublevel set g omega. So this is this green function at W, and we have a sublevel set. So that's the kind of the main result I want to talk about today. When this result is really interesting when this t is going to minus infinity. Yes? Yes. Yeah, if I present a result that is not mine, that I give you the name of or names of the authors. So if t is very small, then this sublevel set is a very tiny set near the pole. In fact, it's the shape of it is closer and closer to the ball. But this is getting large. In fact, there is a general conjecture, maybe I have a few minutes to tell you about that this expression is monotone in T. That's only proved in dimension 1. But that's okay. Now, this is completely optimal because there is, for example, if you take a ball centered at W, then you have equality for all T. Now, but this has some consequences. So first in dimension 1, if you let t go to infinity, then you can easily show that the right-hand side is c omega w square over pi. The c omega w is a logarithmic capacity of the complement of omega with respect to w. Well, whatever. It's really exponent of the so-called Robin constant. Robin constant is this. Okay, I don't want to talk too much. I have no time to talk too much on this. But this was a so-called Suita conjecture that was proved only, well, relatively recently, originally by some different methods. But so this is just to show you that this result is already non-trivial in dimension 1. Okay, well, maybe I should just write what c omega w is. This is exponent of the Robin constant. So limit as z goes to w, g omega zw minus log z minus w. So and this corollary is immediate from the theorem. But I think it's even more interesting what happens. Oh, okay, I have to finish quickly. What happens when omega is convex? Okay. So maybe if that was corollary 1, so let me call it corollary 2. So if omega is in Cn convex, then it follows that k omega w is bounded by 1 over the volume of I omega w, where I omega is the Kobayashi indicatrix of omega. So this is of all phi prime at the origin, where phi is a holomorphic disk in omega. So this is a holomorphic mapping between this is the unit disk, and this is omega. Omega is in Cn. Well, such that 0 at the origin goes to w. So to prove, I mean, this corollary follows from this theorem using this Lampert theory. But it also, the point is that that's really the limit of this thing when t goes to minus infinity. But now, in fact, this lower bound in the Nazarov theorem follows very easily from this corollary proposition, because one can show this was that. So when omega is this tube domain, so when omega is so if omega, so K is convex symmetric body. I will not write it again. So omega is a tube for K. So then this indicatrix as a set is contained, well, with some constant, I think 4 over pi, in K plus IK. So therefore, the volume of this is bounded by right constants times the volume square of those, and therefore you immediately get that lower bound. Okay, I should maybe finish in 1 or 2 minutes. So two things. One, the proof of this really uses the bar equations. So that's I have no time to talk about that. There are at least now three proofs really of this result. Initial proof was first to prove a more rough estimate using an estimate for d-bar due to Donnelly and Pfefferman, and then use a procedure so-called tensor power trick. So take a Cartesian product of these domains many times, and if you go with the dimension to infinity, or the product number of copies to infinity, you will get the optimal constant. But there is another proof due to Lempert using Bergson theory, so-called direct positivity of direct image bundles, some more advanced stuff. But somehow everywhere there is a d-bar equation hidden. Another thing is that for convex domains, there is also an upper bound with a constant. So the upper bound is with a constant 4 to the n, and this is more elementary, and this is joined with Zvonek, and we don't know what an optimal upper bound is for convex domains. And finally, what I mentioned, that the open problem is whether this expression in T, it should be kind of, the estimate should be optimal when T goes to minus infinity. And so that's a conjecture that it's monotone in T. And so with Zvonek, we proved it for n equal 1. And it's very funny. The proof is not very difficult, but it follows from the isoperimetric inequality. And really, in higher dimensions, it's kind of equivalent to some version of complex isoperimetric inequality that we don't know how to prove. Okay, maybe I should finish now. Thank you very much.
Time for questions or comments. Professor Markiewicz.
I was highly impressed by the application of complex variables bigger than 1 to number theory, because Mahler's conjecture, I knew Mahler, of course, was a number theoretician, and this conjecture actually belongs to geometry of numbers. You see, Riemann was the first who applied complex theory, complex functions in one variable to number theory, and now the time to apply, several variables.
But not Jacob.
Yeah, so it's really, it's kind of, I think, a breakthrough of Nazarov that found this link.